Hey guys, this is Vijay. Today on the screencast, I'm going to be explaining how to do a two-dimensional electric field problem solving because some people are still confused about the problem solving part. The question which I'll be explaining is a question that Ms. Vijay handed out in class on the worksheet Electric Fields 2. The question is, a 0.060 kilogram electrically charged ball hangs at the end of a string oriented 53 degrees outward from a charged vertical plate. The E field produced by the plate at the position of the ball is 1.0 times 10 to the fifth newtons per coulomb, and points away from the plate. Complete the table that follows to determine the charge on the ball, the sign, and the magnitude. Assume that the gravitational constant is 10 newtons per kilogram. Generally it's 9.8, but for the purpose of this question, we're asked to use 10 newtons. And the diagram is shown below. As you can see, the mass is the white circle and it's oriented 53 degrees outward from the charged plate. Okay, so the first thing we need to do is draw a force diagram for our question. So we know that there's going to be three forces acting on the mass. One is the tension, or the force of the string on the mass. But since the string is acting on an angle, this force is also on an angle, therefore it has an x and a y component. Then there's the force of the electric field in the positive x direction. And then there's the force of Earth on the mass, which is in the negative y direction. The angle above the horizontal is what we need to know to solve the question for the x and y components. So it's normally going to be above the horizontal axes. So it would be 90 plus 53 degrees, which was the given angle, which is 143 degrees. But for the sake of keeping everything positive, this degree is also equivalent to 37 degrees in the positive first quadrant. We also know that the net force on the object is going to be zero because the mass isn't moving, it's at rest. Thus, it's a fairly simple problem. We just need to balance our forces and solve for our variables. So as I said before, we're going to solve for our variables in our x and y direction. Since the force on the string, or the force diagram in general, has an x and a y component, we can split up these components in net forces in the x and y direction. In the x direction, we have that the force of the string on the mass times cosine 37, which gives it the factor, is equal to the force of the electric field. The force of the electric field is equal to the value given, 1.0 times 10 to the fifth newtons per coulomb, times the charge of the mass. And as you can see, since the charge of the mass will have the units coulomb, you'll have newtons per coulomb times coulombs, which will factor out to be just newtons. And this is how you get the force of the electric field. So as you can see from the force diagram, in the x direction, you'll have right here the x component of the force of the string, and then you have the force of the electric field. We don't include the force of the earth in the x component. Then in our y direction, we have the force of the string on the mass in the y direction, which is in this case sine 37, is equal to mass times gravity, and the mass is given as 0.060, and the force of the earth, we are told to use 10 newtons per kilograms. We can also notice how in both cases, for the net force in the x and y directions, I have separated the force of the string on the mass in both cases, because this value is a constant between the two sets of equations. It's just that its respective vectors in the x and y direction make them different. So at the end, we can set these two values equal to each other because they're the same number, and we can solve for our charge of the ball. So as I said before, we can set these equal, and then it's just some simple algebra. We set that the first equation equals the second equation, then we can multiply, cross multiply, and divide by our respective numbers, and we get that the charge equals 7.96 times 10 to the negative 6 coulombs, or 7.96 microcoulombs. So all in all, in general, when we're approaching these two-dimensional electric field or electrical problem-solving questions, there's a similar approach to all of them for any of you who are still confused. So the first thing we should do is, regardless of the question, we should always draw a force diagram because there's always going to be some kind of forces interacting with the mass or the system. Next, since it's a two-dimensional question, there will be an x and a y component for everything. So make sure to divide and separate each of the x and y components when it's necessary. Um, Also, it's not, in this case, we were lucky that the system was at rest, so we didn't have to account for any acceleration of the system. But in the case that the system is in motion, we need to be able to identify this so that we can set that the net force is equal to the mass times the acceleration. Also, a lot of times, like also in the case of this problem, the angle given is not always the angle that we need to use for our x and y components. We need to use the angle with respect to the horizontal or above the horizontal if we want to use sine for the y values and cosine for the x values. If the angle is given with respect to the vertical, the sine and cosine values would be switched. You would use the sine for the x values and the cosine for the y values. So you can always shift around your angles to work around this. And at the end, we need to make sure our answer makes sense, of course. If you end up getting a ridiculously large number, ridiculously small number for your answer, should always go back and check your units, check your calculations, and check whether you missed out on a force or anything. And this is basically just the general idea for solving any of these two-dimensional problems on that worksheet.